请到的第一位 panel speaker 是翟敬立院士他也是今年5月刚刚接任中央研究院数学研究所的所长翟院士是1978年台大数学系毕业的，然后他当兵，然后就出国在1984年在哈佛取得博士学位然后就到Princeton 再过到宾州大学，我想是比较长的时间。他现在也是他们那边的professor我想翟院士是国际上非常有名的代数几何、算术几何专家那我去了台大之后，我听到很多有关他的这个从年轻时候开始的丰功伟业。所以那时候我一直想说，怎么把他找回来但是我们都没有能够成功中研究院数学研究所面子比较大，总算把他找回来了所以今年我就想说那我就拜托他来跟我们讲讲他的这个工作，因为他在国际上这方面是非常有名的他非常的谦和，为人很客气我一拜托他呢，就我的手一爽快就答应所以我想我们今天非常幸运的能够由他来跟我们讲有关他的擅长的领域这个我不一定真的很懂太symmetries reduction of modular varieties 这个对我来讲也是很亲切的事情。我想我今天应该学到很多东西，大家也应该是这个就请翟院士。
Thank you very much, Vera, for the very kind introduction. It's truly a pleasure to be able to attend a meeting and give a talk. The topic today and also the title, I'm afraid maybe a little, sounds too technical. But after thinking about what I should be talking about, I thought that this topic is the one that I have more confidence and have more substance that will fit the occasion. So I said myself, I'll give it a try. And when I started preparing, so somehow I was a little too ambitious. But after a while, it seems that I should only be giving an overall picture. There will be.
Yeah, although there's a list of 9 items, I think I'll get maybe perhaps the 6. Just to give the general picture of the thing, and I'll try to just the emphasis will be the overall picture. There will be certain slides which look very technical, but I'll try to explain what that means. If this is not something you are familiar with, please just let it pass. I hope that I'll give sufficient evidence that will try to make sense out of these. So the general goal of today's talk is to give an idea of what Hecke symmetry is about in characteristic P. So the subject is that we have a modular variety, some algebraic variety. They classify certain objects. These objects are called abelian varieties. And then there are some imposed symmetry on these abelian varieties. And so the algebraic variety one obtains this way is something, not arbitrarily just writing down equations, but rather they are so to speak God-given because they classify certain collections of interesting algebraic varieties. Now, perhaps the most prominent feature of such varieties is that
there is a whole collection of symmetry, a very large family of symmetries operating on such varieties. And they are called Hecke correspondences, and I'll call them Hecke symmetries. They are symmetries, and I'll try to explain what they are later. But so most of the time, when people think about these modular varieties, or sometimes called Shimura varieties, what they do, these varieties live in characteristic 0. For instance, complex numbers. And these symmetries in characteristic P has before the 1990s, or generally have not received that much attention. But there are some reasons, I'll indicate a few, that these are both interesting and have applications. But life in characteristic P, well, is interesting but complicated. And basically because it's not easy to study them by usual topological methods. And so here I list a general question, the general sort of question, giving a flavor. It's that if we are given such a modular variety, we know that there are Hecke symmetries on such a variety. Now, I'll be thinking about some sort of the first sort of question that one would ask if one begins to try to understand what these symmetries do. Okay? So among other things, the question I asked myself a long time ago was this. Suppose think about all subvarieties in such a given variety, and that's stable under all such Hecke correspondences. Now, what are the minimal ones? Well, of course, we want non-empty minimal ones. Otherwise, the problem is too trivial. So that's the question. So these are the smaller things, the building blocks. If one can say anything, understand anything about these symmetries, one should be able to understand them. Okay? Or if one is more technical, so well, you take a point, you take the orbit under all such symmetries, and you ask, what's the Zariski closure? Zariski closure is an operation that from points produce smallest subvarieties containing a given collection of points. So a Hecke orbit is a countable subset of an algebraic variety. And then you take the closure. Now, in usual topology, you may not feel that this is a hard problem. But in algebraic geometry, this is terribly hard. Because algebraic geometry is, in some sense, not set up to answer such questions in an efficient way. Now, so there is a slightly better formulation, which may one begins to think about and attack this, and formulate it in terms of a rigidity problem. Okay. What that is that, well, there are certain invariants. These are p-adic invariants. P is the given prime number, which is the characteristic of the field. And so generally, the idea is this. If we are thinking about Hecke correspondences, so these are symmetries that are defined, or the feature of the way they are defined is that they don't interfere with invariants in characteristic P, or p-adic invariants. So of course, if you have such a smallest invariant subset, any p-adic invariant that's constant on such a variety remains constant. It doesn't change. Okay. And somehow you think very hard, and you can't think of any other thing any other conserved quantity or conserved invariance. Any invariance that's conserved all these prime to p Hecke correspondences. Now, because of lack of imagination, then we decide perhaps there's a fighting chance that indeed such minimal subvarieties that's invariant under all Hecke correspondences is actually just cut out by fixing the values of all p-adic invariants. Okay. And that's the question. And what's the present status? Well, there are in certain examples, certain situations, one knows how to prove it. But there are much more situations where one can't. What that means, of course, is that we don't really understand this problem. The reason that we can prove something in certain situations is that in certain situations, we have some tricks in our sleeves. Therefore, in these special situations, with the help of certain tricks, we can do it. But what we aim for is, of course, to understand the problem sufficiently well in order to really understand and do this problem. And somehow, of course, the goal is not just to answer this question. The goal is to understand the symmetries themselves. And because the symmetries are extremely important, they come in various places. So if we thinking back, what have we achieved? It's really that the new method that we developed, one sort of understand things well, and then you get some way to understand the situation. And that's what a good problem should do. And so one of the benefits of doing this is that suddenly we get a collection of new methods that allows us to do something in other situations. And one of them is that there is a set of tools developed to handle the geometry of modular varieties in characteristic P. I hope to get to some of that. And also there are applications in number theory, especially Iwasawa theory. Okay. So now I hope to I'll begin to do something a little technical, because I don't want to just wave my hands. So I would like to define what they are. I apologize, but this is a little technical. But before I do that, I would like to give a general picture of what such symmetries are like. So here is a simplified picture, and it's easier to describe them in characteristic 0. So that's what I'll do first. We start with a bounded symmetric domain, and that's D. And so generally, the way a bounded symmetric domain is given is that the real point, which is a Lie group, called G here, operates transitively on this bounded symmetric domain. And then, so inside this Lie group G, which is a real point of G, we take an arithmetic subgroup. The standard sort of picture is that the bounded symmetric domain is a Z. A discrete subgroup of finite covolume. And so we have a discrete group operating on D, and D mod gamma. Gamma is the name of this discrete subgroup. It's quite large. So it has a natural structure as an algebraic varieties, and this is a standard example of arithmetic quotients of bounded symmetric domains. Now we have taken the group gamma, that's a bounded symmetric domain gamma. Now it seems that then, after this step, we have lost all symmetries. So before one took the quotient by gamma, the whole group, the real points G of R here, operates on D. But once one goes to the quotient, then there's no action anymore. But fortunately, or I mean the standard phenomenon, is that we didn't lose all of them. There's some remnant of this action. What's that? You think about, you think about any point, which is in this case a Q point, meaning that it's a 2G by 2G matrix, and so inside the symplectic group, G is a symplectic group. So and they have entries. All the entries are rational numbers. And then the properties, I mean, that's very easy, and you check that almost very quickly, that if you conjugate the group gamma by little gamma, and that subgroup intersect with gamma itself, is a finite index in both gamma and the conjugation by gamma. And what that means is that if you take the quotient of D by gamma intersect the gamma inverse conjugating gamma. And then you get, so multiplication by gamma defines a map from this slightly bigger quotient to D mod gamma. And if you think about this, what this means is that every element of gamma, every element gamma of this group of Q points defines a finite to 1, and 1 to finite, correspondence on this quotient. So this is, we don't have a group action anymore, but there's a substitute. And that family of algebraic correspondences is the substitute. And that these correspondences is what classical Hecke symmetries or Hecke correspondences are about. And if we linearize such a situation, what one gets, so you linearize meaning that you take some sort of functions on such spaces, or I mean, sometimes you take L2 sections of some vector bundles, line bundles, then the problem becomes linearized, and we get some families of functions, or in some general sense, and then these algebraic correspondences induce linear operators and these generally infinite dimensional vector spaces. And these operators are what's known classically as Hecke operators. So that's the symmetry. Or if one looks upon this, there is a more sleek way of describing the symmetry. Namely, you consider all such subgroup of finite index, they can shrink, so more and more, and you consider, instead of one quotient, you consider the family of all such quotients. They form a natural projective system. If you pass through the system, then not only we have the smaller group operating coming from the group itself and the finite quotients of these, that's what you generally expect from general Galois theory. But rather, you suddenly see that a much larger group in this situation, the Q points of G, that's much larger than groups that you obtain from finite quotients of gamma. They operate on this, and you have this pretty big group operating on this tower, this projective system, and they induce Hecke correspondences on finite quotients. Now, next, I'll be pretty quick in explaining what they are. So the kind of varieties 1 to 10 now will switch to a characteristic P world. So here, for most of the time, we'll be thinking about problems in characteristic P. So in such a field, say for instance, let's say P equals 5. What that means, of course, is that if you add 1 to itself, to take any element in such a field, you take this element and you add this element to itself 5 times, you get 0. I mean, that's the sort of situation that we learned in a course in algebra back in college days. And now most of us don't think about such situation very often. I think, who will be interested in characteristic P? I mean, that they do weird things. But sometimes you're forced to. So instead of justifying what the characteristic P world is like, I mean, I somehow resign to fate. I mean, and so try to think about geometry and in characteristic P. And now, P is a fixed prime number. I'd like to describe to you such the varieties in characteristic P. They are basically, you take a field, a number of variables, and then you take a bunch of algebraic equations. And these algebraic equations define a variety, and that's the general flavor of such varieties. Okay, and so these slides look technical, and what that means is that instead of writing down equation, I'll describe certain classification problem, and then the general theory says that you actually get a God-given variety. They classify the points of such varieties corresponds exactly to the sort of object that one is looking at. The objects here are first we fix a linear algebra structure. I will not go through that, and I'll post my slide, the slides on the web, so you don't really need to take notes. Okay. Just keep in mind that this is some linear algebra structure, and then I'll be looking at algebraic varieties whose first homology group is modeled on such a given linear algebra structure. And these are called PEL type modular varieties. P stands for polarization, E stands for anamorphisms, and L stands for level structure. It's basically we're specifying a type of symmetry on an algebraic variety, and we want to classify all of them. And that you can do, so because of time, sorry, probably this is flashing too fast, but don't mind. So it's something that you can define by linear algebra, okay? And what the part of the structure is a complex structure, linear algebra. So what it does is that these complex structures in characteristic 0 define abelian varieties, because abelian varieties are complex tori which emit a polarization. Now, when we fix a prime number P, we assume that's unramified. I'll suppress what unramified means. So it tends to give good reduction. Okay. And then when you look at the situation, there's a general theory which tells us that indeed there is an algebraic variety which classifies. Okay. And inside, for such a thing, the symmetry group is governed by the given linear algebra data. So there is a group, a linear algebraic group or a matrix group, which comes from the linear algebra data. And they operate from there are many symmetries arising from this group that operates on certain towers of such variety. So we'll take the prime to P tower. These are, if you make the level structures smaller and smaller, well, then when you get just like the characteristic 0 situation, you have a projective system of modular varieties, and then the Galois group of such a cover is a compact group. Okay. So let me switch down to give what the compact group is. So the compact group is a projected limit of finite group. So I mean, so you take points inside this thing. This is a compact thing, and you get a compact group. Okay. And the problem, or the magic, is that although the Galois group is a compact group, which is we think of as being small, once one passes through the whole projective system, a very large group, these are essentially the Q points of this group, just like in characteristic 0, operates on the whole tower. And these symmetries, these large group, induce symmetries on finite level, namely the moduli space M itself, and they induce Hecke correspondences, or Hecke symmetries, on the original moduli. Okay. I'm sorry that I can't do, because of time, it's not possible to give really more precise definition. So this is just an impressionistic description of what these moduli spaces are and what these symmetries do. Okay. So let me go very quickly over to show that there are some examples. The typical and the first class of examples is the Ziegel modular varieties, and they classify G-dimensional principally polarized abelian varieties with a principal level structure, with certain level structure. In this situation, we'll take various prime to P level structure. Level structure means that you rigidify torsion points on the abelian variety. Okay. So here is a standard sort of picture that we saw before, and all I want to do here is that in this situation, the formula for the action is the classical one that we are mostly familiar with, except now that ABCDs are G by G matrices. They satisfy certain conditions so that this matrix preserves the standard alternating pairing. And the action of this symplectic group on the upper half plane is given by the classical formula. And this is the picture in characteristic 0. Okay. Now, what's the difference between characteristic 0 and characteristic P? It's a whole lot. Now, if you take a point in a moduli space, the moduli space in characteristic 0, essentially we can understand pretty well, especially its usual topology, by going through the representation of its complex points as a quotient by bounded symmetric domain. If one asks, so what are the orbits of Hecke correspondences are like? You say, well, you think about it, and you just say, well, this is just trivial. So it's such an easy question. You take a point, and you operate on it by the Q points of the group. But the Q points are dense in the real points. So with any topology you care to think about, it's dense. It's dense in a very, very strong sense. Okay, so it's trivially dense. There's no, but life in characteristic P is somehow more perplexing, richer, interesting, depending on your taste. Now, the main reason is that there are certain invariants that you don't see in characteristic 0. You only get to see them in characteristic P. And these are what I call p-adic invariants. And the Hecke symmetries that we think about, because they are prime to P, they preserve these symmetries. They preserve these p-adic invariants. So suddenly, you get many more subvarieties which are preserved under all Hecke symmetries, because these p-adic invariants can assume many, many values. And in fact, these values vary, possible values vary in continuous parameters. So for instance, certain orbits can be finite. And the familiar case is the case that G is equal to 1. And what that means is that we are thinking about elliptic curves. Elliptic curves in characteristic P come in two varieties, two sorts. One, the standard one is called ordinary, but there are certain, so not so general one. These are called supersingular. So let me, oops, the supersingular, and so there is the difference is whether a certain invariant called Hasse invariant is 0 or not. And the side note, which I found out much later in my professional life, is why these things are called supersingular. So such names seems to indicate that people who gave these names don't have much imagination in naming objects. And the historical reasons is that if an elliptic curve has complex multiplication, I mean people call that their J invariants singular. So now there is a singular for another reason, so they are called supersingular. Now, so there is another class of examples. So they are called Hilbert modular varieties. They are attached to totally real number fields. If you fix for yourself a totally real number field, and think about abelian varieties whose dimension is equal to the degree of this totally real field, and you look at abelian varieties of that dimension with action by the ring of integers of this totally real number field, and the modular variety one gets is called the Hilbert modular variety, first defined by Hilbert. And again, so here is we have a symmetric group operating on it, and the symmetric group is essentially the SL2 group, but with entries in the total real field. Now, let me spend maybe a few minutes on possible p-adic invariants attached to abelian varieties. If you are given an abelian variety in characteristic P, now, so there is a construction. Which in characteristic P is a pretty good substitute for the Lie algebra. Taking Lie algebra, the Lie algebra of an abelian variety in characteristic P, unlike the characteristic 0 situation, carry very little information. Now, what one does is to think about the system of all torsion points whose orders are powers of P. Okay? And this collection, this is an inductive system, and such an inductive system is called a p-divisible group. And this is the source, well, the only known source, and in fact, in many ways, the only source of p-adic invariance. When you pass from an abelian variety in characteristic P to characteristic from abelian variety to the p-divisible group, in some sense, we are doing a localization process and somehow retain the p-adic invariance, but nothing else. So if you like, the isomorphism class of this the p-divisible group attached to an abelian variety in characteristic P, in some sense, is the ultimate p-adic invariant. Okay. And here are some examples of p-adic invariant. So you think about how Frobenius, we learned Frobenius in algebra. Frobenius is the map sending an element in a field of characteristic P to its P's power, or P's squares power, or power, or P to the nth power. Okay. And then, so these induce maps between, so from this given a p-divisible group or abelian variety to itself. Okay. And then one has certain elementary divisors for such a linear map, and you look at the p-adic valuation of these elementary divisors. What you get is a collection of 2G rational numbers between 0 and 1. They satisfy certain duality properties, and these are called slopes. Okay, and so the easiest example is that the first G of them are 0, the last G of them are 1, and then, well, obviously, they satisfy such duality condition, and this is sort of the majority of abelian varieties in characteristic P. They are called, such abelian varieties will be called ordinary. Now, on the completely opposite side, the other extreme, we can have all of them equal to 1/2. And if that's the case, we say that the abelian variety is supersingular. Now, supersingular abelian varieties have very special properties, but for the benefit of time, we'll skip that. So here, what I would like to explain is to convince you that there are certain ways to do a local construction. I won't be very specific, although sort of the slides give the details. What basically one does is that you take an abelian variety, and then you pass to the localized object, which is the p-divisible group. Okay. Now, over the in such a local situation, there are two groups in p-adics that's of interest. One is that you take endomorphisms of these abelian varieties. The other is that you take endomorphisms of the associated p-divisible group. And once you look at them and can produce groups using the structure of semi-simple algebra with involution. If you use the abelian varieties, you get a smaller group. If you use p-divisible group, that's the localized object we just talked about, and the structure is softer, and we have more endomorphisms. Okay. And what happens is that there's some general theory, deformation theory for abelian varieties, that tells us that instead of looking at a whole modular variety, we look at its infinitesimal neighborhoods, or technically the formal completion of the modular variety at that point. And what happens is that both of these groups operate not on the whole modular variety, but in the formal infinitesimal neighborhood at this given point. And the standard example, if you want to know what they look like, you look at a formal torus, which is given by the formal power series ring over a characteristic P field. And the coordinate y secretly represents the point 1 plus y. So that the endomorphism ring is just all possible powers. And what do they do? It sends the coordinate y to that correspondence. What that really means is that 1 plus y should go to the nth power of 1 plus y. That's the standard power. So this is what these local symmetries sort of tends to look like. But in general, it's much, much more complicated. And you don't want to write a formula for it because that's too hard. Okay. So there's a bigger group, and then there's a smaller group, h of x, and the smaller subgroup is, for many good reasons, is the intersection. We can think about them as the intersection of the global Hecke symmetries with the local symmetry group. Okay. And then, if you have some subvariety stable under all Hecke symmetries, then of course it's stable under the local version of this. Now, my time is flying through, so I'll suppress some of these examples. Okay. So let me tell you, I have about 10 minutes left. Let me tell you, now that we have introduced the actors or the scene, so what are the general problem? Okay. The prediction is that if we have a subvariety stable under all prime to p Hecke correspondences, then it basically is a leaf. What's a leaf? It'll be explained in the next slide. But essentially, what that is that you fix all p-adic invariants. Okay. And so these are the building blocks for subvarieties stable under all Hecke correspondences. And in many ways, the leaves themselves should be thought of as Shimura varieties in characteristic P. Okay. So here is that a leaf, you fix all p-adic invariants, meaning that we fix the isomorphism type of the p-divisible group. if you remember, I said that the p-divisible group is the ultimate p-adic invariant. Okay. So here are some examples. So let me just do one of them in the interest of time. Is that if we go to think about ordinary abelian varieties in the Ziegel modular variety, then it's a leaf. I'm sorry, I'll pass through these other examples. There's no time for them. So here the remark is that there is actually some stronger versions of the global rigidity problem. Recall that the global rigidity problem is that if you have a subvariety stable under all prime to p Hecke correspondences, it's a leaf. Now, the stronger version basically is that, well, if we weaken the assumption, we don't know, we're not given that it's stable under all Hecke correspondences, but rather just a portion of them. Okay. And then you still want so a very, very strict, very precise prediction of what they can be. And in certain situations, is that this is a reasonable thing, and this is what you expect. Now there's a corresponding local version of the problem. The local version is that, well, we pass to the local setting so that we have a formal variety, and we assume that it's under its state in the formal completion of a point, namely the infinitesimal neighborhood of a given point. We're given a formal subvariety, and we assume that it's stable under the action of a portion of the local symmetries, but not too, but the local symmetries are not too small. And the prediction is that the subvariety will be a very, very special form. And let's see. Now, so let's sort of say a few things about what's known. So here is a proposition. What it means, what it says is that we generally have very good ideas about the formal completion of a leaf as a subvariety of the formal completion of a point of the modular variety. Okay, and here's an example of the typical thing. So I introduced what I call the baby example, and now you take R copies of the baby example, and you ask which subvarieties of a formal torus is stable under a single anamorphism. Okay. And remarkably, you can say something even under these very weak conditions, namely, it's a formal subgroup. It's a formal subtorus. That's the kind of local rigidity one is after. And now, finally, I get to state in a very rough form of what one can do. Okay. The first thing one can say is that, well, after years of effort, in fact, we can say something, at least in one class of examples, one can show that the local rigidity actually holds. And the proof uses a result in a crucial way, a result of Cha-Fu Yu, who is presently at the Institute of Mathematics, a colleague of mine, a former student. It's a pleasure. And so the reason that the Hilbert modular variety enters the picture, that's the result of Cha-Fu, is a Hilbert trick. So basically what the trick says is that if we have an abelian variety over a finite field, then its Frobenius defines a complex multiplication structure on this abelian variety over a finite field. So in other words, somehow it's that when you live in characteristic P, you have this extra map, a God-given map, which is the Frobenius, and the Frobenius does wonders. But this trick fails, and that's in general, and that's the reason. So there are lots of situations one cannot understand the problem well enough, and that's the challenge which remains ahead. Okay. And so the strong rigidity for Hilbert modular variety is also true. And so now let me see, we have 3 minutes. So I'll just say that this is among the tools that one developed for doing such kind of problem is group theory. Group theory is useful, although when we were learning algebra for the first time, we don't realize that. So basically, by group theory, one can, for instance, prove that if you have a subvariety stable under all Hecke correspondences, now we want to show that it has only one irreducible component. Now, this tends to be a hard problem in algebraic geometry. But when you have a group theory to help us, so it can be simplified to the following. You can look at the set of all irreducible components. That's a finite. That's often, most of the time, it's a finite set. Now, in such a situation, if you want to show that there's only one irreducible component, I mean, by doing some group theory, one finds that it suffices to show that the symmetries operates transitively on this finite set. And that's one of the things, one of the tools one developed. There are some other situations, some other geometric results one can prove using these tools. So what this says is what this theorem says is that very strong reproducibility results hold. In the following form, so if you fix the slope is 1, it's a simple sort of p-adic invariant. And if the slopes are not all equal to 1/2, you get a subvariety, which in fact is reducible. I mean, this is easy to say, but it's not easy to prove. Just because you're proving how many irreducible components are there in a given set is hard. So for instance, if you write down a polynomial, and then you look at equations, and your polynomial equation, even in one variable, knowing whether the polynomial is irreducible is not that easy. Okay. And the second is that if you fix a leaf that's fixing all p-adic invariants, you get something that's irreducible, as long as not all of them, not all the slopes are supersymmetric. And moreover, one can prove an irreducibility results by raising levels in characteristic P. So this is usually stated in a form that the p-adic monodromy representation, so this is how the Galois group operates covers of such a variety by putting in rigidifications on p torsion points. And if the monodromy is surjective, it means that if you do this, the variety it remains irreducible. So this is a relative irreducibility statement, and that also holds. I think it's probably a good idea to stop here. Thank you for your attention.
Is there any question or comment? Okay, we thank again for Professor Tan for the wonderful